Welcome everybody to the last session of this ONEPAS before the junior talks. So the last speaker is going to be Jiaqi Yang from Georgia Tech, and she's going to talk about invariant objects of infinite dimensional systems.
Thank you very much. So before my talk, I would like to thank all the organizers for this wonderful series of seminars, and thank you all for coming. So I'm going to talk about invariant objects of infinite dimensional systems. And everything I'm going to talk about is a joint work with my collaborator, John Jimeno, and my advisor, Rafael Daleave. Here's the outline of the talk. I will first introduce the problem, and then I will talk about our main results, and then provide a sketch of the proof, and then talk about some examples. After that, I will talk about a specific case, which is delay equations, which appears in electrodynamics. So delay differential equations are not like ordinary differential equations. Delay differential equations are differential equations where the right-hand side depends on the solution at the previous time. One simple example of delay differential equation is this equation x prime of t equals to f of x of t minus 1. Unlike the ODE case, right now it's not enough to just prescribe the value of the solution at time t equals to 0 and then solve for positive time. Right now we have to prescribe a continuous function on some interval. And right now, because the time delay is constant 1, we have to prescribe a continuous function defined on the interval -1, 0, and then we are going to propagate forward to get the solution for positive time. And therefore, this is an infinite dimensional problem. And in many applications, one have to consider the so-called state-dependent delay equations, where the delay is no longer a constant. It depends on the current state of the solution, or it depends on a segment of the solution, as we will see later in the examples. And for state-dependent delay equation, is much more complicated than the constant delay equation. One of the complication comes from the right-hand side. As we can see here, there is the composition between the solution X with itself. And one of the origins of delay differential equation comes from the study of electrodynamics. So when we study the interaction of charged particles, the effect between charged particles are not instantaneous. So basically, we will have some kind of equation of this format, and then there are some short delays appearing. Basically, we have this small factor 1 over the speed of light in front of the expression. And for this kind of delay defined implicitly, we're going to see that we are able to deal with it. So among other questions, there are two main questions to be studied for delay differential equations. One is to clarify the phase space and then study the evolution. The other one is to study the invariant objects like periodic orbits, quasi-periodic orbits, invariant manifolds. And for delay differential equations with constant delays, they are better studied. And here are some classical books by Hale and Worden-Lunel, and then also by Dickman, Van Gils, Worden-Lunel, and Walter. And for state-dependent delay equations, they are much more complicated, and even the natural phase space is not clear. Sometimes we consider initial conditions just as functions defined on some interval, but this could generate some non-physical solutions. However, many advances has been made, and one can see the summary of results on state-dependent delay equations by this nice survey by Hadnon, Christine, Walter, and Wu. So basically what people do is that people consider the upper bound of the delay functional R, basically the C0 norm of the delay functional R, and then they will consider functions defined, like let's say the upper bound is like a positive number h. People will consider like C1 functions defined on the interval -h to 0. And in Walter's paper, people were he was kind of considering a submanifold in the space C1 C1 functions on -h to 0. And then he proved that the semi-flow is C1. And there are other works about differentiability of solutions with respect to parameters by Hartmann and Turi. And it seems like there are no results on high regularity of smooth dependence on parameters. So as one example of the invariant objects, periodic orbits are studied extensively by many mathematicians. So for example, in a collection of works by Malapert, Nussbaum, and Paraskevopoulos, I apologize for my pronunciation, and also the work by Seiber and Jacquet, Lessard, and Michael. And some computer-assisted proofs are considered in the work of Vanderburg, Grostady, Lessard, and Stelina and Linzinski. So as mentioned previously in the lectures of Professor Dallave, Professor Gideon, Professor Aro, parameterization method is very useful when we are studying invariant objects. Basically, we study the functional equations satisfied by the parameterization of the invariant objects, and then we just study the function equations. So in previous work of Li, He, and Dallave, they considered quasi-periodic solutions for delay differential equations. And in a previous work, we also considered the case for limit cycles and slow stable manifolds when we add the delay perturbation to a planar ODE. So what we obtained was kind of like a finite dimensional submanifold of the infinite dimensional stable manifold of the periodic orbit, which was considered already in the book of Hale and Warden-Lunel. Okay, so as for today, let us focus on the case for periodic orbits. So we will start with a smooth ODE, and we'll assume that this ODE has a periodic orbit before adding the perturbation. And then we will consider a perturbation of the above ODE, and then the perturbation term depends on this x sub t, which is a segment of the trajectory. So this x sub t is standard in the study of delay differential equations. It is defined by this formula x sub t of s equals to x of t plus s. So so basically, people will consider like h is an upper bound for the delay functional, like the C0 upper bound for the delay functional, and then people usually do is to consider the s to belong in the interval -h to 0. But right now we are considering the space where we can take s to belong to -h to +h, where the h is to be understood as the maximums of all the delays or advances that we consider. So we can not only consider backward delays, we can also consider forward delays, where the equation depends on, like, where the right-hand side of the equation depends on a future state of the solution. And in our study, this h actually can be infinity, like in many models with memories, like when we are modeling the materials with memory effects. And for the time being, we'll assume that this x sub t belongs to some space of smooth functions, and we will specify the space later. Notice that this is a very singular perturbation, because after the perturbation, we will have an equation where we have to prescribe some functions as the initial condition. So it becomes an infinite dimensional problem rather than for the ODE, it's just a finite dimensional problem. So one example for the perturbation term P is like this. Here we consider a function, we still call it P, and then it depends on the current state and depends on the state at the previous time, and then depend on parameter gamma. And to ease the discussion, we will just assume that the function P and the delay function R are both C infinity. And our goal is to show that for small enough epsilon, the periodic orbit of the ODE will persist under perturbation, and also the periodic orbit will depend smoothly on the parameter gamma. To achieve this goal, we will use the parameterization method. We first consider the unperturbed equation. So since we assume the unperturbed equation has a periodic orbit, so we start with a parameterization of the periodic orbit of the unperturbed equation. Basically, we start with a periodic function, which whose image is the periodic orbit of the ODE. This is equivalent to saying that for any fixed theta, this expression k of theta plus omega 0t solves the unperturbed equation, and this omega 0 is the frequency of the periodic orbit. And this is equivalent to say that the frequency omega 0 and k0 satisfy this functional equation 3, which people usually call invariance equations. And I want to emphasize here that the solution, the parameterization, is not going to be unique, because if k0 is a solution to this functional equation 3, then we can consider a shifted phase. Basically, we can define a function k1 such that k1 of theta equals to k0 of theta plus theta 1. So it will still solve this equation 3, but this is the only source of non-uniqueness. Okay, now if we consider the perturbed equation, we are going to think about the parameterization of periodic orbit in a similar way. So basically, since the perturbed equation is a functional differential equation, it's an infinite dimensional problem. So the periodic orbit should also be an infinite dimensional object. However, what we can do is we can do an identification such that the infinite dimensional periodic orbit agrees with a periodic function with values in Rn. So to be more precise, we consider any fixed theta, and then we consider this expression k of theta plus omega t similar to before. And this omega is again the frequency of the periodic orbit. And then we let this expression to solve the perturbed equation. And this is equivalent to, if we plug this expression into the perturbed equation, this is equivalent to this frequency omega and parameterization k satisfy this functional equation 4. And so when we say we have a parameterization of the periodic orbit, this is exactly what we mean. Like we can find omega and k which satisfy this functional equation 4. And notice that this calligraphic P here, it comes from plugging in this expression k of theta plus omega t into the perturbation term in the perturbed equation. So if we come back to the example of state-dependent delay equations, this calligraphic P is just the function P evaluated at k of theta, and evaluated at k tilde of theta, which is a little bit complicated. It involves the function k composed with itself. It comes from the delay. And then it also depends on this parameter gamma. So before talking about our main results, I will talk about assumptions. So let us start with assumptions on the periodic orbit of the unperturbed equation. So for any fixed initial phase theta 0, we consider this fundamental solution of the variational equation of the ODE around the periodic orbit k0. So phi of theta 0 satisfies this equation, and then it also satisfies this initial condition. So our assumption on the periodic orbit of the unperturbed equation is that we assume the monodromy matrix has only simple eigenvalue 1, which corresponds to the tangential direction of the periodic orbit. So one example that hypothesis H1 is satisfied is when the amplitude equation has a hyperbolic periodic orbit. And of course, one case that hypothesis H1 cannot be satisfied is when there exists a conserved quantity for the amplitude equation. So this assumption H1 can be formulated using functional analysis. We can define this operator L on the continuously differential functions which are periodic, and then it is defined using this expression. So the hypothesis H1 is equivalent to the hypothesis H1 prime, which basically says that the range of L is codimension 1 and it's complemented by the tangential direction of the periodic orbit. And we are going to see H1 is equivalent to H1 prime in the proof. Now let us talk about assumptions on the perturbation term. So for any given positive integer L, we are going to consider the space we will call the CL plus Lipschitz space, which contains functions which has continuously continuous which has bounded derivatives up to order L, and the L's derivative will be Lipschitz. The reason why we consider this kind of space is this space is closed under the C0 uniform norm. And we are going to define this CL plus Lipschitz norm by taking the maximum of the subnorms of the derivative and also the Lipschitz constant of the L's derivative. And we need to make two assumptions to get the persistence of periodic orbit. The first one is what we call this H2.1. It's basically, we will refer to this assumption as propagated bounds. It basically says that this calligraphic P maps a CL plus Lipschitz ball around the unperturbed parameterization K0 to a CL minus 1 plus Lipschitz ball. This is we allow one loss of regularity because, as we will see in the operator that we define, we are going to use some integration which allows one loss of derivative. And of course, this hypothesis H2.1 is similar to the a priori bounds in PDE, in the study of PDEs. Okay, we need another assumption on the perturbation term. So we will need that the H3.1 is basically about the calligraphic P is locally Lipschitz in terms of the distance between omega and the C0 difference between K and K prime. So I want to emphasize that this K prime is just another trace of K, and omega prime is another trace of omega. It does not mean the derivative. So, we have a question, I think. Let me pause for a minute.
The question is asking, what is the geometric meaning of those assumptions in the phase space? And what is this periodic orbit isolated or non-degenerate for the ODE?
Oh, yes. So I think this question is about the hypothesis H1. So in this case, basically because we cannot allow conserved quantity, so the periodic orbit should be kind of isolated and it should be non-degenerate. Okay. But here, this hypothesis H2.1 and H3.1 are hypotheses on the perturbation term. Okay, so now we will see these two hypotheses are verified easily for the state-dependent delay example. So recall that for the state-dependent delay example, we have our calligraphic P in this form. So since we have already assumed that P and R, they are both C infinity, so we can just use the composition lemma, which like if we take two CL plus Lipschitz functions, then the composition will still be CL plus Lipschitz. And for the second hypothesis, it follows from like the bounds for the term P and R and their derivatives. So basically, more precisely, we can plug in K and omega in the calligraphic P and also K prime and omega prime in the calligraphic P. And then we can do the standard trick of add and subtract. And then in each of the lines on the right-hand side of the inequality, there is exactly one place where the two terms are different. So for example, in the first line, here we have K, but here we have K prime, and everything else is going to be the same. And now we are ready to use the bounds on the perturbation term P and on the delay function R and their derivatives to get hypothesis H3.1. We will need one more set of assumptions for the smooth dependence on parameters result. So this is this hypothesis H2.2 and H3.2 are very similar to hypothesis H2.1 and H3.1. So now we just need to view the parameterization K as a function of the parameterization variable theta, as well as the parameter gamma. And now we view the frequency omega instead of being a constant, we view it as a function of the parameter gamma. So this H2.2 basically says that in a neighborhood, in a CL plus Lipschitz neighborhood of K0 and omega 0, then this calligraphic P will be CL plus Lipschitz in the parameter gamma and CL minus 1 plus Lipschitz in the parameterization variable theta. So we allow one loss of derivative in theta because we are going to use the integration. And we also assume, similar to before, some bounds on the derivatives. The second hypothesis over here, it's similar to before. Right now, it's still the C0 locally C0 Lipschitz property, and the norms appears on the right-hand side are all C0 norms. Now we are ready to state our main results. Our first results talk about the persistence. It says that if we have the assumptions on the periodic orbits, basically the monodromy matrix has simple eigenvalue 1. And then we have the assumptions on the perturbation term P, which was the propagated bound assumption and C0 Lipschitz assumption. And under these assumptions, we know that if the perturbation is small enough, then there will be a periodic orbit for the perturbed equation. And we can find the parameterization of the periodic orbit of this function K. And we also know that the frequency omega for the new periodic orbit is going to be close to the frequency of the original periodic orbit. And also we are going to show that the parameterization of the new periodic orbit are going to be close to the parameterization of the periodic orbit of the unperturbed equation in the sense of CL norm. And of course, this is like we have chosen a suitable choice of the phases. Otherwise, it makes no sense to compare those two things. And the smallness condition depends on, of course, the unperturbed equation and also the perturbation term, and also the regularity that we are considering. So in general, if we want to have like higher regularity, if we want to have larger L, then we will have to make the epsilon 0 to be smaller. And therefore, basically, if we just look at this theorem, it does not give us C infinity result automatically. But in many cases, in applications, one is able to use the bootstrapping to get C infinity of the periodic orbit. Now for our second result, it says that if we assume the hypothesis on the periodic orbit of the unperturbed equation, and also the hypothesis on the perturbation term, the propagated bound, and the C0 Lipschitz assumption, then we can find a periodic orbit which are parameterized by this K sub gamma and the frequency is omega sub gamma. And this K sub gamma is jointly CL plus Lipschitz in theta and gamma. And the frequency omega gamma is CL plus Lipschitz in gamma. Let me pause a little bit to see if there are any questions. Okay. So here are some remarks of our result. The proof is based on constructing an operator, and the operator maps the CL plus Lipschitz ball into itself, and it is a C0 contraction. Therefore, we know that there exists a fixed point, which is also in the CL plus Lipschitz ball. And since this proof is constructive, it leads to algorithms. And thanks to the contraction, one can also get a posteriori type of result. A posteriori type of result states that if one can have, if one has some kind of approximate solution, under some conditions, there will be a true solution to the equation close to the approximate one. And this type of result is widely used in validating asymptotic expansions. Asymptotic expansions are formal power series which are not known to converge. And it is widely used in the case where small delays arise. For example, in this paper by Ciccone, and also in this other paper by Casal, Corsi, and Dall'Ave. And this kind of a posteriori result can be used to validate that the asymptotic expansions are approximations of the true solutions. And this a posteriori type of result can also be used to validate numerical results. In a previous work, we were constructing calculations for the limit cycle and its low stable manifolds to delay perturbations of a planar ODE. Now let me give a sketch of the proof. Recall that right now our goal is to solve this functional equation, which we call an invariance equation. And since we expect the frequency and the parameterization are going to be close to the unperturbed ones, so we do this kind of regrouping. Omega equals to omega 0 plus k hat, and k equals to k0 plus k hat. And then we are using the invariance equation of k0 and omega 0, and also the invariance equation of omega and k. We are able to get this functional equation to be satisfied by omega hat and k hat. And they are the only unknowns in this equation 7. If we look at this equation 7, the left-hand side is just the operator L evaluated at this k hat. And the right-hand side is kind of small. So the B epsilon in the right-hand side, it's small. It contains 3 terms. The first term in B epsilon is the quadratic term in this expression f of k0 plus k hat. And the second term in B epsilon is the perturbation term epsilon times calligraphic P. And the third term is this term which is quadratic in omega hat and k hat. So we are going to define an operator whose fixed point will solve this functional equation 7. We are going to do that in 2 steps. The first step is we adjust the frequency. We adjust this omega hat such that the right-hand side of this equation 7 lies in the range of the operator L. And the second step is we just invert the operator L. Basically, we will use the variation of parameters formula. Before introducing the operator, let me talk about some notations and the space that we are going to define the operator. So at a point k0 theta 0 on the periodic orbit, there exists a spectral splitting, the tangential direction of the periodic orbit, and a space E sub theta 0, which is of dimension n-1, which corresponds to the eigenvalues of the monodromy matrix, which are not 1. And we are going to denote the projections onto these two spaces as pi tangent at theta 0 and pi perp at theta 0, although these two spaces may not be perpendicular to each other. So now we will consider an interval around 0 and a ball in the CL plus Lipschitz space of periodic functions defined on the circle. So the interval I is going to be the space for omega hat, and the calligraphic B is going to be the space for K hat. And the constants A and betas appears in this definition. We are going to choose them in the proof. Right now, we are going to define operator on the space I cross calligraphic B. Following the two steps that I was mentioning, we are going to update the omega height by this first component of gamma epsilon. Basically, this first component of gamma epsilon will get rid of the tangential component in this B epsilon. And we are going to update the parameterization K hat by using this second component of gamma epsilon. Basically, this is the variation of constant formula using the updated omega height. So as we can see here, we are using an integration which allows the loss of one loss of regularity. And this notation U0 is the initial condition for gamma epsilon sub 2. And we choose it to satisfy this equation, which is equivalent to this gamma epsilon 2 is periodic. And we also choose this U0 to be in the space E sub theta 0. If we do not let U0 to be in this space, then there are infinitely many solutions for this equation for U0 up to a scalar multiple of the tangential direction. And choosing such initial condition U0 will correspond to a shifted phase. For our proof, we first need to have this lemma on propagated bound. It says that if epsilon is small enough, then we can choose the constants in the definition of the interval I and the function space B, such that the operator maps I cross B to itself. So since this I cross B is actually compact and convex subset of the real cross the continuous functions which are periodic, then based on the assumptions, we also know that the operator gamma epsilon is actually continuous. So once we have this lemma, we are ready to use Schroeder's fixed point theorem to obtain the existence of the fixed point. And actually, the assumption H3.1, which was about the C0 Lipschitz condition, can be weakened to just some continuous properties. But right now, we are still going to show that the operator is a C0 contraction in order to get uniqueness of the fixed point and also to get the a posteriori bounds. The basic idea for the proof of the previous lemma is as follows. Basically, we first consider C0 bounds. To consider C0 bounds is enough to consider this expression. And recall that this B epsilon is small, so the first term in B epsilon can be controlled by the C0 norm of K hat squared. And this dk squared, this norm appears here is the C0 norm of the second derivative of f in a neighborhood of the unperturbed periodic orbit. And the second term in B epsilon can be controlled by just assumptions on the calligraphic P. And the third term can be controlled using integration by parts like this. So if we kind of proceed inductively, we see that the nth derivative of the second component of gamma epsilon is an expression which contains derivatives of B epsilon up to order n-1. So so we can allow one loss of regularity in this calligraphic P. So we can just choose the A's and the betas recursively to make sure that the operator gamma epsilon maps the space into itself. For our main result, we need another lemma, which is about the C0 contraction. So we define this kind of C0 distance on the space I cross B. So this lemma says that if the epsilon is small enough and the constants A, which appears in the definition of the interval I, and this beta 0, which appeared in the definition of the space calligraphic B, they are all small enough, then the operator is a contraction on I cross B under C0 norm. In order to show this lemma, it suffices to consider this difference over here. So recall that the first term in B epsilon is kind of quadratic, so it can just be controlled by adding and subtracting terms. And notice that this K hat and K hat O prime, the C0 norm of them can be controlled by beta 0. And the second term can be controlled by the C0 Lipschitz assumption on the calligraphic P. And the last term is over here, and it can be controlled by integration by parts. And this recall that this can be controlled by beta 0, and the absolute value of omega hat prime can be controlled by A. So once we have these two lemmas, we know that there exists a fixed point in the space I cross calligraphic B for the contraction gamma epsilon. And if we use K0 plus K hat star, we will have a parameterization of the new periodic orbit. And omega 0 plus omega hat star is going to be the frequency of the new periodic orbit. And if we choose initial guess for omega hat and K hat as omega hat 0 and K hat 0, then based on the contraction argument, we know that if the first iteration of omega 0 hat and K hat is close by, then the fixed point will also be close to the initial guess. And this will provide us the a posteriori estimates. And if we choose the initial guess for omega hat 0 and K hat 0 at 0, 0, basically we just take the frequency and the parameterization of the periodic orbit from the amplitude equation. Then we will see that using this inequality, we will see that K and K0 are close in C0 sense. However, since we know we have controls on the CL plus Lipschitz norms, therefore we can get up to CL estimates of this distance between K and K0 just using interpolation. To get a smooth dependence on the parameter result, everything is the same. Basically, we just view the omega hat, instead of being a constant, we view it as a function of parameter gamma. And we view the parameterization K as a function of the variables theta and also the parameter gamma. And then we define the operator in the same way. And then we show that the operator maps the space into itself, and it is a C0 contraction. Therefore, we have the fixed point for the operator. As a corollary, one can consider the time periodic case. Here, the amplitude equation is periodic in time and with frequency omega 0. Now we can consider exactly the same perturbation as before, or we can consider some perturbation which depends on time. The only constraint is that if we are considering some time periodic perturbation, then the frequency should agree with the frequency of this function f. And similar to before, we still consider the solution to the variational equation around the periodic orbit with this initial condition. And instead of the assumption H1, which says that the monodromy matrix has simple eigenvalue 1, we just assume that the monodromy matrix has no eigenvalue 1. And the proof of this is actually easier than before because we do not need to adjust the frequency. We already know the frequency for the periodic orbit of the perturbed equation. So we just need to define an operator to update the parameterization k hat. And again, this U0 is chosen in such a way that this upsilon epsilon is periodic in theta. The general result led us to consider more complicated state-dependent delay equations. For example, one can consider delays which depends on a segment of the solution and also on the parameter gamma. And one can also consider distributed delays in terms of an integration. So we can get the calligraphic P in these cases. And then if the calligraphic P satisfies the assumptions that we imposed, then we know our results will apply. And let me emphasize that our results are not limited to one delay or one advance. The perturbation can involve several delays or several advanced terms. Now we are ready to talk about the small delays and electrodynamics. In many applications, one has to consider equations with small delays. And here we consider the autonomous case and also the time periodic case. And as we will see, this time periodic case will be useful when we consider the electrodynamics. And here the delay function R is the delay functional. Yes. So it can take many forms. It could be a constant, it could be time dependent, it could be state dependent, as long as it satisfies the two assumptions. Basically, we need propagated bounds and then C0 Lipschitz property. Our main result for the small delay case is like this. So we will assume that the equation is like CL plus Lipschitz, and then we will still assume like the assumptions on the periodic orbits of the unperturbed equation. So in the autonomous case, we assume the monodromy matrix has simple eigenvalue 1, and in the non-autonomous case, we assume the monodromy matrix does not have eigenvalue 1. And we need the following two assumptions on the delay term. So the first one says that it maps a CL plus Lipschitz ball into a CL minus 1 plus Lipschitz ball in a neighborhood of K0 and omega 0. And the second one is still the C0 Lipschitz condition. And under these three assumptions, we show that there exists a epsilon 0, such that if epsilon is smaller than epsilon 0, then the perturbed equation will admit a periodic solution. And we can also formulate the smooth dependence on parameter results in a similar manner. And we are going to skip that for now. Let me talk about the idea of the proof. I will take the autonomous equation as an example. The non-autonomous case will be similar. So we do this add and subtract in order to put the equation in the form of our general setting. And this difference over here can be expressed using this integration form. So this is our perturbation term P. And by plugging in the K of theta plus omega t, we can get our calligraphic P, which is also in terms of integration. However, right now, it's not a direct application of our previous main results because there is no problem on the propagated bound assumption on this calligraphic P. But there is some problem when we consider the C0 Lipschitz assumption because of this decay term. So this calligraphic P is not Lipschitz in terms of C0 with respect to K. but we can define the operator in the same way as before, and then we're going to prove like two lemmas similar to before. Just for the contraction, we just need to use integration by parts to take care of this decay term. Now we consider a model of uncharged particles in electrodynamics. So here, this Qi means the position of the ice particle. And this AEXT means the time-dependent external force field. So for now, we cannot consider like autonomous external force field because there will be a conserved quantity. So the hypothesis on the periodic orbit cannot be satisfied. And this Aij, it is just some algebraic expression. We are not going to specify it here. It means the impact of the particle J on the particle I due to the Leonard-Wishart potentials. And one can see more details about this in the book of Classical Electrodynamics by Jackson. And I want to emphasize that here, this Aij can also include other relativistic forces. As we can see here, we have some delay term, and which are defined implicitly by this equation. So here, this c is the speed of light, and this, as we can see, this delay tau ij contains this small factor. So our goal is to apply the result for the case with small delays. Okay, and what also in total, we have many delays. In total, we have n times n-1 delays. So now what we are going to do is we are going to consider the positions and velocities of all the particles, and then we are going to use the results of the small delay. We have to show that the delay term tau ij satisfies the assumptions we made on the delay term in the case of these small delays. So in order to do that, we have to make two assumptions on the trajectories. The first one is that the speed of a particle cannot reach the speed of light. The second one says that there are no collisions. So we are able to show that if these two assumptions on the trajectories are satisfied, then the delays satisfies the propagated bound assumption. We have some control on the CL plus Lipschitz norm of this tau ij by the CL plus Lipschitz norm of the trajectory. And it also satisfies the C0 Lipschitz condition. The proof of this proposition is based on realizing the right-hand side of this equation in defining this tau ij is actually a contraction in tau ij, and then using implicit function theorem. And I want to emphasize that here we have this small factor 1/c, which help us to apply the results in the small delay case. C is the speed of light. So here is our main result in the case of electrodynamics. If we let epsilon to be 1/c, we assume that the periodic orbit for the amplitude equation satisfies the assumption H1 double prime, which says the monodromy matrix does not have eigenvalue 1. And we also need assumptions on the trajectories, the two assumptions on the trajectory, one on the speed and the other one on no collision. Then under these assumptions, all the expressions Aij are going to be analytic. So we just need to assume the regularity on this external force field. And we have shown that if the perturbation is small enough, then we have a CL plus Lipschitz periodic solution. And there is also smooth dependence on the parameters. In summary, we have used the parameterization method and also the fixed point approach to get persistence of periodic orbits and smooth dependence on parameters in many settings. And let me emphasize that the same philosophy works for other things. For example, quasi-periodic solutions, and also in a previous work, we were discussing the limit cycle and the slow stable manifold of a perturbation of a planar ODE. And here are some works in progress. We are also considering perturbations of evolutionary PDEs. And we find these two books very useful, one by Shriskov and the other one by Wu. And one can also consider perturbations of delay differential equations, because the main strategy that we use is the propagated bounds and C0 Lipschitz condition, and it also works for infinite dimensional spaces. And with Jean-Philippe Lessard and J. James, we are also working on computer-assisted proofs of the results that I've talked about. And we hope to come back to these questions in the near future. So we are also trying to prove high regularity of center manifold in perturbative setting. And this will justify the beautiful work of Calleja, Humphreys, and Kroskov. And we want to consider the persistence of periodic orbits when there is a conserved quantity. And we also want to consider bifurcation. And of course, our ultimate goal is to get rid of the perturbative setting. Thank you all for your attention.
Everyone can unmute themselves now.
Great. Are there any questions or comments for the speaker?
Yeah, I have a question. Comment.
Sure. Go ahead.
Yeah, this is Carmen Ciccone. For the case where you have a conserved quantity, as I recall in the classical perturbation theory, it's the derivative of the period function for the periodic orbits in a family that is the non-degeneracy condition. That should replace your H1. Is that the way you would approach it? The case where you have a conserved quantity? Did I make myself clear?
You're muted.
Actually, could you repeat the question? Sorry.
Well, it's sort of a question and comment. So in the case where you have a conserved quantity, one of the cases would be where you have a one parameter family of periodic orbits, and then you want to make perturbation from that. So in the classical theory, the non-degeneracy condition is that the derivative of the period function at the periodic orbit that persists is not zero. Maybe that could replace your H1 condition. I don't see it. So my question is, do you see an obvious impediment to doing that?
We are still working on that, but I think you are making a very good point. Yes, I think we can use the assumptions that you mentioned. Yes.
Yeah, that probably is the way to do it. Then some reduction technique would allow you to do it. Maybe Lyapunov-Schmidt reduction. Yeah, this is very good.
It's a little bit more complicated than this, because I mean, these things that Carmen is mentioning is when the perturbed system has a conserved quantity also. But now the system is not going to have a conserved quantity either. You see, that's a lot of, so it's when you add dissipations or something. I mean, it's like if you were adding dissipation or something like this, right?
Yeah.
Or something more general. The thing that happens is that the whole family of periodic orbits may collapse into one periodic orbit or something like this. It disintegrates, so to speak, right? So
yeah, that's what I had in mind was
at the beginning you have a whole thing and so on, But then at the end, I mean, if you add a little bit of dissipation, the whole thing could, you know, suppose that you start with something like the family of periodic orbits in a Hamiltonian systems, and then you add a lot of friction, then everything goes away. You see what I mean?
Yeah, so the non-degeneracy condition I mentioned is for that case, right? Where you allow, that's right. And then you might have just one periodic orbit persisting.
Yeah, and then it's so you may have one or none
or none. That's right.
Yeah.
That would be very good to add, because that should work the same way somehow, I would think. Maybe more complicated, but yeah.
More.
Maybe we should work together or something with you.
Well, maybe
that will be nice, because yeah, I mean, it's
More questions or comments or proposals?
So I have a naive question. So you gave this nice physical electrodynamics example of a delay differential equation. I'm curious, are there sort of applied math examples where you have the sort of future seeing differential negative delay differential equations? I don't know what you call these things, oracle differential equations or something like that.
Yeah, I think it appeared in some formulation of Feynman-Wheeler, because they want to require some kind of symmetry. So if you have negative delay, then you should have positive delay as well.
Okay, thanks.
Anybody else? No? If not, let's then thank Jiaqi again.
Very good.
Very nice.
And we hope to see everybody tomorrow with the junior talks.
At 2 p.m.
Oh yeah, that's
so we made it kinder for the Europeans to come.